Welcome everyone. We continue today our exploration of congestion control in the internet. We'll do part 2 of this lecture with a little remainder of part 1. Tomorrow the lab will start where you will be able to explore in the virtual environment everything we see here. There's a caveat though, in the virtual environment things are never as good as in real environments because we are emulating several computers in one computer. And the emulation is never perfect, so what we see here in the lecture in the emulated environment will be true with 10 or 20% margin. Another thing, don't forget to fill in the online evaluation form for this and other lectures. So we receive complaints that the participation rate of master student is very low, so don't hesitate. It's a good system. At EPFL you can say what you want about lectures, good or bad. Hopefully more good than bad, but okay. You'll have to say what you have to say. Don't forget to fill in the evaluation. Internet congestion control is based on the needs to do something to prevent congestion collapse and trying to reach some form of fairness, which maximizes usefulness of the network, utility, while keeping some reasonable balance between the shares that each user receives, and practically is based on end-to-end control. That means it's the sources that try to control their rates. We will see that it's by means of TCP, and it uses essentially 2 mechanisms. One is AIMD, Additive Increase, Multiplicative Decrease, that we've discussed last week, why this one is preferable to other variants of it, and Slowstart. Slowstart is an additional mechanism that I will now describe. So Slowstart is justified by what happens due to the fact that not all connections start at the same time. So the analysis that led to AIMD is a static analysis. That's a criticism that some people make to it. They assume there's a number of flows. At time 0, all the flows are present, and then you want to see how to manage things. And then we can move a bit towards fairness and efficiency. But it doesn't account for what happens in the transient phase, which is illustrated in this simulation here, where I'm showing on this part, on the x-axis is time, and the y-axis is the rate achieved by 3 sources, the red one starting a bit later, and the blue and green one having started before. So they were sharing the network. When the red ones, then the desired behavior of AIMD is exactly this one. So that we share, but only after a number of iterations. Here, I'm showing for comparison the rate of source 1 on the x-axis versus the rate of source 3. Those 2 sources are in the same conditions, so they should reach the same value, but we see that there are large iterations, and when we start here, because source 3 that starts this from scratch has a 0 rate, it takes a number of iterations, which you can count here, 1, 2, 3, 4, 5, 6, 7 negative feedback until the rates are approximately the same. This is how AIMD works. So it works well for flows that are stationary or at least very long. Now, the idea of Slowstart was to avoid this problem by saying, well, if the flows are not too long, which is the case, in fact, for many flows in the internet, except for if you're downloading a streaming video of very high quality, then many flows are not so long. So in fact, they will be in this phase, and then you stop. So if you do this, that means that you will not be competing with the long flows that are not competing dynamically enough. The idea of Slowstart is to be fast. So it's a misnomer, and it's often misunderstood. Slowstart is a fast start. What is slow in Slowstart is that we start from 0 or from a minimum rate, 2 packets per round trip time. In that sense, it is slow. But if we do this, we would have some slow start. The goal of slow start is to say we would like to very quickly go to the middle here. We start from below. That's minimum it's wise to do it if we want to avoid congestion. We don't want to allow a connection to start at any arbitrary rate. We start from 0, but if we just apply AIMD, it will not converge fast enough. So it's an empirical finding that leads us to try to improve it. So the idea of Slowstart, which was developed at the same time as the rest of congestion control, is to apply multiplicative increase, which we saw is not a good thing to do in stationary regime, but if you want to go very quickly to a good rate, you increase exponentially or multiplicatively, which means for every positive feedback that you receive, you multiply the rate by a constant factor of 2. So it's far from slow start here. And you do that until you believe you have reached the same fair share as others, which, in the case of slow start, is by detection of negative feedback. So you exit slow start when either you receive negative feedback or when you, sorry, not when you receive negative feedback, when the target rate is received, and we will see what the target rate is. Target rate is illustrated on this window. So with slow start, we have two variables that describe the rate at which we are sending. One which is the current rate, like any rate control algorithm. That is the plain line here. And another one, the dashed line, is the target rate, sometimes called, if you look into the Linux code, it's called the slow start threshold. In my slides, I call it the target rate. It's one and the same. So if I am a source, then I would like to have a target rate initially that is as high as my system allows, so my local approximation of plus infinity. And then I will increase my rate exponentially by seeing if I receive positive feedback until I hit negative feedback. When I hit negative feedback, this is where I believe I've been able to sense the capacity of the network. So when I do this, I reduce my rate to half the current rate. So we see on this line, the current rate was around between 5 and 6, whatever the units. Then I apply additive increase, multiplicative decrease to the ideal rate that I think I have reached at that point. So I go very fast until I am like the others. And when I am like the others, I've hit the limit, so a bit like nasty children who always exaggerate until you hit them and they stop. And from that, the system, from that roll, you play the same game as before. So you reduce your target rate by half. This is why the dashed line here is at 2.5. And then you will try again to increase exponentially. We could have set the rate here, but the designer's choice was to say, well, if you hit that rate, you restart from slow start exponentially. And then you will exit that game whenever your target rate is equal to the rate you have achieved. So here it happens after receiving one loss. So this is the algorithm that does exactly what I said in algorithmic form. Yes?
What are the benefits of restarting? And don't we lose times?
Here?
Yeah.
It's a good point. Why do we restart here and not go immediately to half the rate? That's a design decision, and some people have objected to it because it may slow down it does slow down the system. So it's a conservative approach to say we are in the black, in the dark, we don't know exactly at all what the target rate should be. Should it be 0.5 kilobit per second or 20 megabit per second? Depends on the congestion state. So it's a bit risky to have a very high rate because we might have been lucky here and reach a very high rate by accident. So by doing that, you are more conservative. But you're right, it causes poor performance at the beginning, which you can see very often. If you try to download something with a TCP connection that employs this, if you're unlucky and you have several phases of this, it takes a long time, contrary to what slow start would like to do, to reach a good rate. And if you have a different piece of luck and your first loss is a bit later, then you would be much better off. Yes?
Why do we reduce the target rate to half of 6?
Well, the intuition behind that is nothing than an intuition, right? There's no mathematical model other than the intuition that says we're trying to compete with other sources that are already established and do AIMD, Additive Increase, Multiplicative Decrease. So in order to compete with them, we try to go very fast. We increase we could start at a very high rate and see how much we lose. But this would be non-cooperative. So we start from a small rate, we increase very rapidly. And the belief is that if we have no loss, that means as long as we're increasing and we receive no loss, then we are not hitting the capacity of the network. So we're not hurting the network, so therefore probably our rate is below the fair share we should receive. Or the network is not congested at all, so we can increase. And only when we hit a loss, then we have sensed the water. We have seen where the problems are. Now, which target rate should we get? At the beginning, we don't know. We take plus infinity or the max allowed by the system. But when I have received a loss, I have some information about the network. I know I had received a loss when I was sending at this rate. So now I have already pushed myself among the others. I have created a loss, probably. It's not sure, everything is random here, but the interpretation is I have created a loss, I've caused the capacity to be exhausted, I've caused the total rate to go above capacity. Therefore, I should start from this value. I was sending at 5 megabits per second when the loss occurred, so I am like another AIMD source. From that point, I employ AIMD. That's the motivation. So this exploration phase has led us to discover in which range the capacity is. Here it's around 5 and not around 1 million, for example. Here is the same simulation as before. This is what we had seen a minute ago at the top. Now if I employ Slowstart on the green source, then we see that in 1 or 2 iterations it quickly gets to the same rate as the others. In fact, slightly above. But it very quickly goes into the same region as the others. That's the intention. So if you are not the green, the red source trying to compete with others, you see that very quickly, in very few cycles of negative feedback, you will be playing with the others. This is what Slowstart is about. So we have seen all elements that are in the internet, AIMD and Slowstart. Now let's see in practice how this is implemented, which is the topic of part 2. Part 2 is about TCP, primarily, because congestion control is implemented in TCP. And as usual in TCP, there are many complexities. So we've seen all the complexity of TCP as a transport protocol. Now we add to the transport layer function the congestion control function. So sometimes people say we have a congestion controlled transport, and it comes with a bit of complexity that I'll try to tame by explaining things one by one. Part of the complexity will be easier because we have seen already the rationale behind AIMD and the other elements. So the first thing is congestion control in the internet, which is, remember, retrofitted, was not initially designed, came as an afterthought after seeing a catastrophe, a congestion collapse, was added. So where do you add congestion control? Well, the idea, it was in the middle of the 80s. At that time, the idea was, well, most flows that are long are using TCP. There was no video on our even internet telephony. Therefore, congestion control comes from TCP flows, people downloading big files. And since we screwed things a bit, we should have put that in IP, but there's no rate control in the IP layer. So let's put it in TCP. That was the first element of this consideration. The second element is we need feedback. The feedback, this is the Y variable that we receive throttle the sources, how do we get the feedback? Well, a very important decision was to see, well, negative feedback is a loss. Whenever TCP senses a loss, then we declare this is a negative feedback. And acknowledgement is positive feedback. So this is how it works. So how can we control the rate of a sending source? Well, approximately, we've seen that with TCP, the rate at which a TCP source sends when there is no loss is approximately equal to the window size divided by the round-trip time. It's an approximate formula because the round-trip time itself is not a constant entity. It varies in particular with queuing, but that gives us a first-order approximation and understanding on how things are. So the idea of congestion control is to control the window. The window in TCP is already controlled by the advertisement. If I'm a TCP sender, I receive window fields in the TCP headers on the return path that I should use to give the size of the sliding window. In addition to that, a TCP sender maintains another variable, which is usually in the code called CWND, congestion window. And then the size of the sliding window is the minimum of the two constraints. One is the congestion window that we have. The other is called the offered window. That's the window that we find in the TCP headers, which, if you remember, is present in order to protect the buffers at the receiver. Do not send more than the receiver can buffer. So that's the main thing. Once we have that, then we can easily guess how things are done. Whenever we receive a loss, we detect a loss, we decrease the window size by 2, approximately. We will see there's a number of details that make that a bit more complex. And whenever we receive positive feedback in the form of acknowledgements, we perform some kind of additive increase, which means we add something to the window size. And we also do slow start at the beginning of a connection. Now, for reasons that are more historical than anything else, when there is a timeout in TCP, some people believe that timeouts are rare in TCP because we have fast retransmit and selective acknowledgements. So if we have a TCP flow that works well and losses are rare events, then we should detect them by fast retransmit. If we detect by timeout, it means fast retransmit did not work, and this is interpreted as a bad sign, a sign that there is very severe congestion. For example, you start losing all your packets. And if you lose all the packets, then there will be no fast retransmit, because fast retransmit requires that you receive a number of ACKs, but there are gaps. Not everything has been received properly, but there is a flow of ACKs that is coming back to you. So the network is in normal condition, you're just hitting the capacity. Now, if something really bad happens, for example, there is a surge of traffic and the capacity is all of a sudden very different per user, or there has been rerouting, we went from a high-speed link to a low-speed link, whatever the condition, that should cause a timeout. That's the belief. As a consequence of this belief, if we sense a timeout, we consider that we should reset everything and we go into slow start, which is how TCP works today. So if we combine those two things, here is how we can view the lifetime of a TCP connection. So here, this is showing as a function of time, essentially round-trip times, the size of the window maintained by congestion control in TCP. It's not in bytes, it's in k bytes here. It's taken from this paper here. And we see two windows. There is the real window, congestion window, and the target window or slow start threshold that is used during slow start. So you recognize at the beginning that the window is increasing, the congestion window is increasing. This is the slow start phase until we reach the end of slow start, which occurs at point A here. So if we zoom, and then after you've exited slow start, we see a slow increase of the window size which should be linear if we had additive increase, but things are never like theory in TCP. I'll explain why. It's linear at the beginning, then it stops a bit, and then there is a loss at time b that causes a reduction of the window size by 2. But if we zoom at what happened on b, we see that in fact the window, the black, which is the true window size, is not exactly reduced by 2, but because this loss was detected by timeout, the window size, we go to slow start again. But while going into slow start, we set the slow start threshold, or the target window, to half of the window size. So that's a bit complicated. It's simple if you make an approximation of it, where you consider that what is happening here is that I have a phase where I am increasing practically linearly. Then when I feel a loss, which is the theory of AIMD, I divide the window by 2. Now there's a small transient period in which the window is actually smaller, but we do approximately, it's like dividing the window by 2. Why in this case here do we have something that is not exactly like in theory? For example, why is it linearly increasing and then it stops? Well, that's because the computers are not sending steady streams of data. It may be, for example, that the source has sent a large bulk of data and then has nothing else to send, and one packet was lost. So the assumption of fast retransmit is the source is always retransmitting, is always transmitting things. Now, what happens if the last packet or one of the last packets of your block is lost? Then fast retransmit will not work. And because it will not work, perhaps it's the last block, so you have nothing to send. So even though the window could increase, but since you send nothing, you do not get acknowledgement. If you don't get acknowledgement, the window does not increase. So this is one of the reasons. In other words, one of the reasons we see a discrepancy is that by controlling things with a window, we're just doing an approximation of rate control. We're not exactly controlling the rate. I mean, a window gives a rate only for a source, one that has no loss, and second, that is constantly sending. If it's more bursty, then the rate, the interpretation of rate is only very approximate. Another approximation is how TCP does multiplicative increase, and additive increase. Multiplicative decrease. Sorry. Multiplicative decrease is done by reducing the window size by 2, so this is not an approximation. Additive increase is an approximation. Additive increase we should do per time unit. Now, what is a time unit? In the model we saw last week, there was a discrete time model. We were in the world of academics. We have a model with discrete time, and then we do theory. Now you're in the world of the computer. You go from the model to reality. What is the time unit? So generally for TCP, people take as time unit the round trip time. So we should increase per round trip time by a constant amount. That's the additive increase. Now, how do we do that? Well, we could measure the round trip time and do an increase per exactly round trip time, but it's done in a different way, which is more adaptive and more subtle. It consists in doing this adaptation. For every positive acknowledgement received, by positive acknowledgement, I mean an acknowledgement, a packet that contains an acknowledgement that moves the acknowledgement field, not a repeated acknowledgement. I increase the congestion window by MSS squared divided by congestion window. So MSS squared, MSS is the maximum segment size. Segment is the TCP PDU, TCP packet, so it's a TCP packet that fits in an IP packet. Right? Now we find here, I mean the language that we find here is already pointing to a discrepancy in the different elements of theory. TCP is a streaming protocol, so TCP views bytes. But the analysis of congestion control is done on a per packet basis. Everything I've shown was a very simplified model. So people have reasoned thinking of packets. And so there's a discrepancy. The two things don't fit well together. The way we try to make them fit is to assume that we have a long-lived flow that will send packets of maximum size, which is not guaranteed. So there's a maximum size, which is usually negotiated at the beginning of a TCP connection. It's called the MSS. It's typically 1400 and something. And now if I rescale this equation by changing the units, so the window of TCP is in bytes, even though congestion control reasons in packets. So if I take the same equation as here, but I count in packets, assuming for a second that the packets are all of constant size equal to 1 MSS, then this update becomes congestion window measured in packet is incremented by this, so MSS square. So I need to divide by MSS, and I need to divide also the increment again by MSS. So if I rechange the unit, it gives this. If I count in packets, it means I increment by 1 over the size of the window for every positive acknowledgement received. Yes?
You mentioned time unit is round trip time, but the round trip time also changes time unit.
Yes, and the round trip time also changes, which is another source of approximation. But this is what is done. So what is the intention? Well, the idea is that if the congestion window would not change within a round trip time, what are you doing? Well, during the time it sends to send a full window, you double the window. So you increase the window size by a full window in the time it takes to send an entire window. So which is illustrated here on this diagram. So here the window size is assuming 1, or so it's 1 at the beginning. Then I receive 1 packet, so I increment by 1 over 1, which gives me 2. Now we'll cheat a bit. This is what we see in the documents that describe this, but the math is a bit different. Now assume I do this update, but I do a lazy update. I keep the value of congestion window at the beginning at time 2 here, which was 2. So for every acknowledgement I receive, I increment by 1 over 2, which is cheating. And the second time I should increment by 1 over 3. Okay. But assume this is how we would do it. If we would do it, then the window becomes 3. And then once I have received a full window of 3, the window will become 4. Okay. In fact, it will become a bit less, depending on how this is implemented. Now, if you look at the Linux code, very often it's implemented not for every ACK that is received, but periodically you look at how many ACKs you've received. So this is closer to what we've done here. And other implementations might do things a bit different. Now, if you look at this diagram, you will see that for every full window size, I've incremented by 1. Which is a bit less than additive increase. With additive increase, we would increment by 1 for every round trip time. Now, the time it sends to send a full window and receive the ACKs is a bit more than round trip time. It's the round trip time plus the transmission time. So we increment by a bit less, but that's the intention. And this is how additive increase, in fact, slightly sub-additive increase, is implemented in TCP. But the first order factor is that we, roughly speaking, increment by 1 MSS per round trip time, as a very crude approximation. We will see that this analysis has some implications. So this is how additive increase is approximately implemented. Multiplicative decrease is in the same vein. Now we increment by 1. If we count in packet, for every acknowledgement received, we increment by 1. When do we do multiplicative increase? It's when we're in Slowstart, typically. So when we're in Slowstart and we do multiplicative increase, we increment by 1. And if we do the same kind of analysis, we see that in approximately round trip time, the window doubles. A bit less, but approximately in 1 round trip time. So this is how this is implemented in TCP. So we see it's based on AIMD, we add Slowstart, then we do all those approximations. So it's hard to predict what happens in reality, but we will see we can still try to understand the performance of TCP. So if we summarize things, here is the typical life of a TCP connection where losses are detected by timeout. We have a phase of additive increase, which is as long as we don't lose data, as long as we don't have any loss detected. Then we have multiplicative decrease, which is not very visible. The multiplicative decrease is in fact the reduction from the plain line to the dotted line. And then we have slow start that comes in addition here. This is, as a first approximation, how TCP works. Sometimes we can give it a finite state machine description, which is most of the time how TCP is implemented. So in addition to all the bells and whistles we've seen 3 weeks ago about TCP, a TCP sender needs to do all that stuff. It needs to know, am I in slow start or in what is called congestion avoidance? The terminology is perhaps the most difficult thing in this story because it's not very clear what it is alluding to. I mentioned slow start, which is a fast start. And then the additive increase phase is called congestion avoidance, which is not avoiding congestion because you're increasing your rate. This is how it's called. And then the multiplicative decrease is not perceived as a phase, but as a phase transition. Multiplicative decrease occurs when we move from slow start from congestion avoidance to slow start. So the phases that are perceived by the designers of this system are slow start and congestion avoidance. This is an incomplete description because here I've assumed all losses are detected by timeout. We'll explain in a few minutes what happens in the other cases. But before that, it's time for you to be a bit active. And resurrect your clicker. Five seconds. I close the poll. And of course, the majority thinks that the TCP source thinks it is a congestion loss and reduces its window. And that's exactly the drama of TCP and congestion control on the internet today. Yes, the answer is yes. If there is a loss due to something else than congestion, typically mobility, wireless links, even if you don't move, things are moving around you. So even a purely static environment makes things mobile for the radio propagation medium. And it's very hard for the MAC layer to be sure to repair all losses. The only way if you could have a very, very low error rate on the MAC layer is to have very, very low bit rates. So you can operate Wi-Fi at 2 or 5 megabits per second and you will have very few losses. But most of the time you prefer to run it at 50 megabits per second and experience more losses. Now if there are losses, TCP will think it's congestion because TCP gets as negative feedback loss. That is the consequence of the design decisions that was done in the middle of the 80s where mobile networks did not exist. And this is one thing that people have been trying to fix over the years, but it's still unfixed today. So this is why at home sometimes you get much worse performance on your laptop on Wi-Fi than on Ethernet, even if the bottleneck is not your local area network, but is your ADSL line. But when you're competing with other people in the internet, you have the losses that come from competition, reduction of rate, division of 2 of your rate, plus all the times you lose a packet on your Wi-Fi. So that is a problem that largely is unsolved today, and we'll see it has implications in lots of places. Now let's see what happens when losses are not detected by timeout, which is the regular thing that should happen. Well, we could say the window is halved, period. Well, that's not exactly what is done. So losses that are not detected by timeout are typically detected by fast retransmit. And then what happens to the congestion window has received a name. It's called fast recovery. Fast recovery means how we interpret a loss and how we do the division of the rate by 2. We do two things. The target window, the slow start threshold, which here is a misnomer. It has nothing to do with slow start. So the target window is reduced by 2. However, the window is temporarily allowed to increase, and in fact to increase very fast, and the reason being to allow the loss to be repaired. The rationale is the following. The interpretation that the rate of a TCP connection is equal to the window divided by round trip time is true if there is no loss. Now if there is a loss, what happens? The window is blocked, and if you have a loss at the beginning of the window, then you cannot send anything. So a single loss might block entirely a receiver. So in fact, when there is a loss, your sending rate automatically becomes much less, even if you don't reduce the window. Now, if there is a loss detected by fast retransmit, we think we should only reduce the window by 2. But if we only do that, in some cases, it might make it very difficult to it might cause a penalty, which is much larger than the reduction by 2. Now, what exactly is the penalty? What is the window size that you should have is impossible to know in practice because we don't know where the loss is. If you would like to do things nicely, you would need either to do a more thorough analysis and analyze where the loss is, or you put a true rate control on TCP, where you interpret the rate and not the window size, which is not done. So instead, what is done is the following clumsy algorithm that is called fast recovery. So when a loss is detected by 3 or TCP max dup ax, which is not always 3, duplicate ax. So here I'm assuming it's 3, which is very often the value in Linux, but Windows often has 2. Then we reduce the target window to 0.5, the current size of the window. That's multiplicative decrease. And then we start a phase of multiplicative increase, a bit like in Slowstart. We start from this window, and then we add 1 MSS per ACK received. If the number of duplicate ACKs that we have received is 3, even for duplicate ACKs here, is 3, then we increase by 3. So we start from the target window plus 3, and then we do this exponential or multiplicative increase until the detected loss is repaired. And when the detected loss is repaired, we forget about all this and we set the congestion window to be equal to the target window. So it looks like the window is increasing very quickly, but remember that doesn't mean the sending rate is increasing very quickly, because as the window size is large, but we have lost packets in the middle, so the actual window that can be used is much smaller than the target window size. That's the rationale. So let's see a small simulation of this. This is showing an example where TCP max dup ACK is 3. At time 1, we are in the so-called congestion avoidance phase. So the target window is equal to the congestion window. In fact, we don't need the target window. And then it increases by every acknowledgement received. And we see that at time 6, for example, the window has increased by 1 over the window size, which makes it 813. All packets are of size 100, which is of course highly academic. So we can nicely send packets, but packet number 1, sequence number 100 to 200, is lost. So sooner or later it will be detected. It will be detected at this point when we have received 3 duplicate acknowledgements. At this point, the congestion window was 813 just before receiving this. So we divide it by 2 and we take this as target. And then we start this little game, a bit like Slowstart, where we put this plus 3, because we have received 3 duplicate ACKs, so we start at 700. And then we increase it for, now the effective window size is the minimum of this and the offered window, which in this example is much larger, so therefore doesn't play a role. But in reality, when we do traces with Wireshark of TCP, We might also have problems on the receiver side that influences the window. This is also another reason for making the practical analysis sometimes very different. But here, I assume the window size is very large at the receiver, so only congestion in the network is controlling the window. So at this point, I am here. The window is 700. Now, the last acknowledgement received was for 200, so I can send until so I guess the loss again, the lost packet must not be that one, right? If we're acknowledging 200, the lost packet is the next one. That's again a mistake I did consistently at least. Now we see that as the window is increased, that allows me to continue sending until eventually here the loss is repaired. And when the loss is repaired, we exit this so-called fast recovery phase, and the congestion window is set to the target window. Let me skip perhaps one thing. Let me skip this one and show, if we do a plot of the window size, then we will see in practice this. So we see that the window increases until there is a loss, and then we have reduction by 2 of the window size and this little increase. But this little increase, as I said, might not necessarily mean the source is sending at a high rate. It may mean so, depending where the loss was, but it does not necessarily mean so. And then we continue sending at this lower rate here. So this is how TCP implements, in fact, additive increase. And if we put all things together, we have this 3-state machine that is implemented in every TCP code for every TCP connection. So you can understand that TCP has a bit of complexity. It's done if you're a web server. You do this 3-state finite state machine for every TCP connection on both ends of the connection, right? On sending and receiving side, because TCP is bidirectional. So we see that we have transitions from slow start to congestion avoidance either when we exit slow start because we have reached the target window, which is the typical case. In congestion avoidance, we do additive increase, and we exit congestion avoidance, typically in fast retransmit. That's the hope. Once in a while also by retransmission timeout that will cause to go to slow start. We exit fast recovery when the expected ACK is received, in which case we go to congestion avoidance. Of course, every more complicated case can occur. You could have multiple losses. So you could, for example, be in congestion avoidance or in fast recovery, and then there are more losses that happen while you're trying to repair some loss detected by fast retransmit. Then you have another timer that expires. That can happen, in which case you go into slow start. Similarly, you can go in slow start several times in a row, in which case there will be a performance penalty. Voilà, so this is the nitty-gritty details of how TCP is implemented. As you see, there's some level of complexity. Now, let's try to understand what we have with this. How can we understand what is happening in the internet when we do all those things? In particular, if we try to forget about the many approximations and we think that as a very crude approximation, TCP is implementing additive increase, multiplicative decrease with slow start to keep things safe. Now, what happens in a network? We've seen that in a network, TCP should try to distribute rates according to some form of fairness. What do you think that it does? Does it implement max-min fairness, proportional fairness, or none of the above? Now, it's a non-educated guess. It's just, what's your best guess? Use the same clicker for two. Okay, so let's see in 5 seconds what is the result of this opinion survey. So the majority of you think it's proportional fairness, with a small minority for max-min, and none of the above. Well, we'll see that the truth is everywhere. And we will see why after the break. So we resume in 15 minutes.